And here we go with the next chapter. Chapter 3 is all about learning about what this derivative thing is that you've heard about before. In Chapter 2, we found the slope of a tangent to a curve using a limit. Well, in this chapter, we're going to learn a shortcut. But first of all, we have to learn the definition of derivative. Okay, what we did before, when we found the general machine that gave us all the slopes of all the tangent lines, when we found f of a, that was actually called the derivative, and I mentioned that in class. Whenever you find the generic machine that tells you all the slopes of all the tangent lines, that's called the derivative. And what we saw was this definition here. Given a function, the slope of the tangent line was, remember we plugged a plus h and a in, where h is some arbitrary very small increment that we're actually going to send to 0. Well, this is actually called the derivative. This is called the derivative. The derivative is a machine that would give you all the slopes of tangent lines. For example, I think one of the machines we saw was negative 1 over, I think it was like 2a minus 1 squared, something like that. This is a function, and you plug in a number, like let's say at x equals 1. Well, so a is 1. So you would do negative 1 over 2 times 1 is 2, minus 1 is 1, 1 squared is 1, equals negative 1. Well, what's the meaning of this? That means the tangent line at the point 1 comma something, the slope of that tangent line is negative 1. Now, how could we figure out this other something? Well, we would have to have the original machine over here. We'd have to know what f of a was, or f of x, and we would plug 1 into the machine. We don't actually have that information in my little example here. Let's move on. Okay, since the derivative is actually a function, it's f of x, we can use function notation, and we don't use the letter m, although I will try to use that some so that you can associate the derivative with a slope. The notation we use is, this is called f prime. It's got the little hash mark up here, f prime. So you say f prime of x. That means the derivative. This is a machine. On my previous page, it would have been this. 2x minus 1, the quantity squared. I just changed the a to an x. So we plug in an x value, and it tells us the slope of the tangent on that curve. Okay, the slope of the tangent on the curve is called the derivative. Okay, let's move on. If the derivative exists, that's how you read this, if there is a slope at a certain spot, then we say that f has a derivative at x, or we use this big fancy word here. F is differentiable, or differential. It should be able, a little typo there, A-B-L-E, at x. If the derivative exists all across the domain, if the derivative exists everywhere on a machine, then we say the original machine is differentiable. It's kind of like when we said this is a separate topic, is f continuous? Well, what does that mean if we say it's continuous? It means if it's continuous at every point on its domain, then f is continuous. Remember this example here. This example here has a discontinuity at x equals 0. However, that's outside the domain. So this is considered a continuous function. Similar kind of concept here. If the derivative exists everywhere in the domain, then we call f differentiable. All right, and we'll be using this term a lot throughout the course of the year, so you'll become more and more comfortable with it. All right, we're going to find our first derivative. Find the derivative of this function right here. This machine is an x to the third machine, so it looks like this. So we're going to come up with another machine called a function. It's called f prime, or the derivative. That's going to tell us all the slopes of all the tangent lines at all the points on this curve. It's really pretty neat. Now this is going to involve a lot of algebra, so we'll try to move through this quickly. this particular example. We have to cube the input, and here is the definition of derivative. Notice instead of having an a here, we put an x. That's the only difference. Last section it was a plus h and a. Now we're actually using x because we recognize, okay, it's on the entire domain, all the x values. All right, so we're going to put the derivative is x plus h. Now our machine is a cubic. We cube the input. So the input we're putting in there is x plus h. So we've got to cube it. Minus f of x, that's just x cubed, all over h. All right, and oh, I forgot the limit as h goes to 0 out front. All right, so now we have to multiply this out. Now remember, this does not equal to x to the third plus h to the third. You have to launch all those missiles. Remember, it's x plus h, and x plus h. And you can actually use Pascal's triangle to do that. And this is going to become x to the third plus 2x squared h plus 2xh squared plus h to the third. And then we have the original, I'm going to make this in blue so that it jumps out here, minus x to the third down here, all over h. And once again, I forgot to put the limit as h goes to 0 up front. You were probably screaming at the iPad right now. Okay, now there's something that cancels. It's the x to the thirds that cancel. And now you take a look. Remember last section, you always factored the h out and it canceled? Well, that's going to happen here also. We're going to get the limit as h goes to 0, h times quantity 2x squared plus 2xh plus h squared all over h, and the h's cancel. Now you can safely plug that 0 in to h. And look here, the only thing that is left standing is the 2x squared, because when you plug 0 in here, this goes away. When you plug in 0 here, this went away. And after all, those h's canceled, so this is the only thing left standing when you actually evaluate the limit. We have just found f prime. That is called the derivative. It is the slope machine. It tells you all the slopes of all the tangent lines at any point on the original curve. So for example, if I wanted to find at 2 comma 8, because after all, 2 to the third power is 8, what is the slope at 2 comma 8? Well, you just come down to this machine. You don't have to do this over and over. You just come down to the machine and you put 2 in there. 2 squared is 4. 4 times 2 is 8. It turns out the slope is equal to 8 there. Well, what about at 327? What about at 327? The slope would be, come down here to our machine and plug 3 in. X equals 3 would be 9. 9 times 2 is 18. The slope would be 18 at the point 3 comma 27. All right, hopefully that made sense. I went through the algebra kind of quickly, so let me know if you have any questions there. All right, there are lots of different ways to say the derivative. I've been saying the derivative. I've been saying f prime. Okay, this is pronounced f prime of x. Well, you can also say y prime, because remember f of x and y are kind of synonymous. Here are the silly ones. This means the derivative of y. It's pronounced dy dx, or the derivative of y with respect to x. With respect to x means that x is the independent variable and y is the dependent variable. So that, again, this is pronounced dy dx. This would be pronounced df dx, or the derivative of f with respect to x. So that means x is the independent variable. All right, this is another fun one. This means the derivative of f. Okay, d dx of f at x. d dx of f at x. Or, once again, the derivative of f at x, where x is the independent variable. So we're going to use all of these different ways, and so will the textbook, so get used to seeing all these notations. They all mean take the derivative. Do it. All right, now this may make your head hurt a little bit. Graphing the derivative from f. All right, so let's fill in the chart down below. Now, at point at point A, I think what this means is the slope is 4. So what we would do, and the point A is at x equals 0, I think you'd agree. The point A is at 0, 1. So what we do is we come over here to x equals 0, and we go up and we record that data. The slope there was 4, so I'm going to put a dot there. All right, let's now go to x equals, oh, by the way, look at the chart here. They're saying, okay, at point B, the slope is 1. So this tangent line right here is up 1 over 1 at B. So I come over here on my little chart and I go to x equals, looks like it's 1.5. So I'm going to go over to 1.5 and I'm going to go up to 1. I'm just recording this data right here, that point right there. Okay. All right, now we're going to move on to the next data point, and it is point C. This looks like the curve actually goes horizontal for a moment. Like if you're coming up the roller coaster, for a moment you're actually flat with the earth. So what that means is a slope of 0. See 0 right there? So we're going to now put a dot at 2, 0. Why 2? Because, look at here, this was at x equals 2, the slope was 0. At x equals 2, the slope of the tangent line was 0. Now at x equals 3, the slope of the tangent line, it says here, is about -1. So we're going to record that data. We go over 3, down 1. Again, this is a slope graph. It's called the graph of f prime. I'm just recording the data. Come over here to point E, which is at 1, 2, 3, 4, 5, 6. It looks like we're at a 0 again. Oh, they say, for some reason it says the slope is still -1. That's fine. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Right here, we're still at -1. And then at point F, I think we're saying, oh, at point F, we are horizontal again. So I'm going to put a dot right there. So now I am going to connect this because, after all, I think you would agree, there are slopes of all tangent lines in between all the points. So we could do more dots, but this is going to be continuous and look something like this. So let me repeat what I just did really quickly. We graphed the derivative, which is a slope machine, by simply harvesting information out of the original graph. And some of it was already given to us. Like, for example, at point C, which is at 2, we were horizontal. So that's why we came over here to 2 and put an x-intercept. So these dots just came from figuring out slopes, or a lot of them were given to us, but we went ahead and graphed f prime from f. This is not an easy task until you get used to it. Okay, so you have to just tear this apart and do it one dot at a time until you see a shape take place like we did here. It looks almost like a parabola or something. All right, now we're going to go backwards. The left side of the screen actually tells us all the slopes of all the tangent lines. So let's look at this. It looks like from -infinity all the way to up to x equals 1, we need to draw something that has the slope of -1. I'm just reading it off of here. It looks like this tells us that the slope needs to be -1. So that's down 1 over 1. So you can actually draw a straight line. This thing has a slope of -1, and it can connect anywhere you want. Then, all of a sudden, the slope of the tangent lines change quickly to 2, up 2 over 1, and this happens at x equals 1. So what happens on this other side, then, is we got to go up 2 over 1 and draw the other half. See, this guy has a slope of +2, and I got that from this number right here. Okay, so it didn't matter actually where we put the graph. It was just that it had to be a V shape where the left side had a slope of -1 and the right side had a slope of +2. I did make them connected, although we'll see later in the year how that didn't necessarily have to be the case here. In this example, we're going to find the derivative again. where our machine is 3 times the input squared, 3x squared. So our formula is the derivative is the limit as x goes to 0 of f of x plus h minus f of x all over h. So here we go. The limit as h goes to 0 on 3 times the input squared, and we're putting in x plus h, and we're going to square that, minus our original function, f of x, all over h. You have to do the foiling on this, the limit as h goes to 0, 3x squared plus 6xh plus 3h squared. I just distributed that 3 while I was going, minus 3x squared all over h. And you now see that the 3x squares cancel, and so do some of those h's. So we're left with limit as h goes to 0 on 6x plus 3h. 6x plus 3h. And then if you plug in that 0 for h, you see that 6x is all that's remaining. And that is actually the slope machine here. It is called the derivative. Let's start by quickly graphing this piecewise function. For x is less than 0, we're on a parabola. This right here is going to be a parabola. So I draw it like this. Okay, that is the parabola. And then, for x is greater than 0, we're going to draw a line that is up to over 1, and of course it has a y-intercept of 0, 0, because 2x plus 0, mx plus b, you can see that goes through there. I want you to notice, let's just look at this graph. Let's zoom in here and look at this. Coming from the right, we have a slope of 2. Coming from our right there, we have a slope of 2. So the right-hand derivative would be 2. The right-hand derivative would be 2 because we're on a constant slope of 2 here, heading towards 0. However, if we're coming from the left, we think we're on a parabola. We are on a parabola. And once we get to 0, we're actually horizontal for a moment. Our slope of our tangent line there would be horizontal. So the left-hand derivative would be 0. So let's see how we would write that. Alright, and there it's written out. On the right-hand side, on the red side, the slopes are constantly 2, which is why I put a 2 there. So the slopes of all the tangent lines are always 2 over here, up 2 over 1. However, on the left side, our slopes are not constant, actually. They're actually changing. And if you do the definition of derivative on x squared, kind of like I did a few slides ago on x to the third, you will get the answer 2x for the derivative. And later we're going to learn a shortcut how to do that. So this would be the derivative on the left. This would be the derivative on the right of x equals 0. All right, good luck on your homework. Let me know if you have any questions.